Hello and welcome to lecture number 3 in our series of geometrical and physical optics lectures. In this lecture we are going to be exploring the subject of image formation in lenses. We are going to learn what a thin lens versus thick lens is. We are going to describe the shapes of 3 typical converging and 3 typical diverging lenses. We are also going to learn about what the f number is and what is a numerical aperture for a lens. We will explain how they control image brightness, and then we are going to move on to the subject of ray tracing techniques and see how they can be used to locate images formed by thin lenses. We are also going to describe the relationship between collimated light and the focal points of a thin lens. We will see what the Lensmaker equation is and how it can be used to determine the focal length of a thin lens. And finally, we're going to look at the analytical approach that's going to be used to determine the location, size, orientation, and the nature of the images formed by simple lenses. So to briefly introduce this important optical component that's used in many optical systems, a lens is a component that's made up of a transparent refracting medium, generally some type of glass, and it's spherically shaped on the front and on the back. It's also important to know that some of the lenses have planar surfaces, so we can have many different types of lens shapes, as the picture on the right hand side shows. Lens is used in many optical devices such as cameras, microscopes, binoculars, telescopes, and this component basically represents a light controlling element that's used primarily for image formation with the visible light, but it can also be used for ultraviolet and infrared light. The picture on the right hand side again shows a few different shapes of lenses. You can see some lenses that have curved or spherical shape or surface, while some of them can have a planar surface on one side. So it's a large variety of different lenses that are used in different applications. Now that we introduced the lens as an important optical component and saw a few different shapes of lenses, let's talk about how light propagates through this important optical component. In a similar way how we analyze the mirrors and use the law of reflection to explain how the light interacts with the mirror, in the case of a lens we are going to be using the phenomenon of refraction and the Snell's law of refraction to explain how the light propagates through the lens. So if we are looking at the picture shown on this slide, we can see the object or the original on the left hand side relative to this lens, and we see a few different light rays that are propagating through the lens. As you can see here, the incident light rays that are coming left to the right and hitting the lens, they are not bounced back but rather being passed through the lens according to the Snell's law of refraction. So first, the ray incident on the front surface of the lens is going to be passed into the lens, it's going to propagate through the lens, and obviously the refraction is going to take place here. As you can see, each of these different incident light rays change their direction, and then the light rays that are propagating through the lens will be hitting the back surface of the lens and then passing back into the air, and then also going to be refracted, meaning they are going to change the direction. It's also important to mention that in this course we're going to be analyzing so-called thin lenses. The thin lens is a lens for which the thickness is very small compared to the radius of the curvature of the two sides of the lens. So once more, a thin lens is a lens for which this thickness t is very, very small relative to the radius of the curvature of the front side and the back side of the lens. That's an important assumption that we are going to take in order to be able to use ray tracing technique as it's explained on the slides that follow. Here we are looking at a few different types of thin lenses. First 3 lenses on the left hand side, as you can see, they are thicker in the middle than at the edges. So each of these 3 on the left hand side, they are thicker in the middle relative to their edge. So these lenses are known as a converging or positive lenses. They cause parallel rays passing through them to bend toward one another and give rise to positive focal lengths. As opposed to the 3 lenses on the left hand side, we also have 3 lenses on the right hand side that are thinner in the middle than they are at the edge. So these types of lenses are so-called diverging or negative lenses, and they cause parallel rays passing through them to spread as they leave the lens and thereby give rise to negative focal lengths. Let's look at the optical properties of the lenses from the perspective of wavefronts. As it can be seen, both for the positive lens and negative lens, we are considering the planar wavefronts on the left hand side and parallel light rays, both for the case of this positive lens here as well as for the case of a negative lens. But you can also see that for the positive lens, the refraction through the lens is going to make the light rays focus onto one single point that's known as a focal point. So in the case of a positive lens, again, the parallel light rays on the left-hand side before entering the lens are going to be refracted in the direction of the focal point on the right-hand side relative to the lens. In the case of a negative lens, however, refraction of light is going to make the light rays diverge from one another as if they originate from the focal point that's positioned on the left relative to the lens. So again, for the negative lens, refraction of the light by the lens causes the light rays to diverge as if it were coming from the focal point F located to the left of the lens. As it can be seen, the focal points of lenses play an important role and are defined in terms of the effect that lenses have on incident parallel light rays and plane wave fronts. Speaking of the focal points for the lenses, it's important to note that as opposed to the mirrors, lenses have two focal points, one on the left side and one on the right side. And here on this picture we have 4 cases, 2 for the positive lens and 2 for the negative lens. We can see how the light rays propagate through each of these lenses and how the light is being focused onto the focal point in the case of a positive lens, as well as how the light rays are diverging as they pass through a negative or diverging lens. We also can see that direction at which these light rays are diverging is as if they originate from the focal point on the left relative to the negative lens. We would like to define here 2 important terms that are associated with the lenses, one being an F number and another term being a numerical aperture. We have already seen that the lens represents an optical component that has a focusing ability of the light. So if the light is coming from the left and hitting this lens, anything that hits this lens over the entire size of the lens is going to be focused onto the focal point. So in other words, the transverse dimension or size of a lens is going to determine its light gathering ability and consequently the brightness of the image it forms. So let's look at the concept of the F number and numerical aperture in a little closer detail on the next slide. So the F number, which is also referred to as the relative aperture of the lens, is defined simply as the ratio of the focal length of the lens to its transverse diameter. So you can see this shutter here that's opening a certain aperture and passing the light towards the lens, and that shutter or that aperture is having a specific diameter that's labeled here as the capital D. So if we take the focal length of the lens and divide by the diameter of this aperture, we're going to get this so-called F number. In this specific case, the F number is equal to 8, so the focal length being 4 centimeters and diameter of the shutter being 0.5 centimeters is going to give us a ratio of 8. So in this case, we are saying that the lens is stopped down to an aperture of D equal to 0.5 centimeters. Obviously, as you're closing this aperture here, less of a light is going to be hitting the lens and less of a light is going to be focused onto the focal point, and consequently the image that this lens is going to be producing is going to be less bright. So again, F number is going to define a light gathering ability of a lens that's going to have a direct impact on the brightness of the image that the lens is going to make. This slide presents the impact of the F number on the light gathering ability of the lens. So you have this table on the right hand side, and you can see here that in the left column you have different F numbers starting with 1 and going all the way up to 22, and for the F number being equal to 1 we have a specific irradiance that is being passed through the lens onto the focal point. And you can see here that if the F number is increased from 1 to 1.4, the irradiance or the brightness or light gathering ability of the lens is basically reduced by 50%. So whatever the brightness was for F number 1, that brightness is going to get reduced by a factor of 2 or down to 50% if the F number is increased from 1 to 1.4. If the F number goes from 1.4 to 2, you can see that the light gathering ability of that lens has been reduced down to 25% of the original light gathering ability of the lens with F number equal to 1. We continue along this table and continue increasing the f number, the irradiance that's being passed by the lens is going to be reduced even further. So to conclude, the image irradiance decreases as the lens is topped down. In other words, the adjustable aperture size behind the camera lens is made smaller so that D decreases. The table on the right hand side again presents the impact on the irradiance as the lens is topped down to larger f numbers. The numerical aperture of a lens is another parameter that determines a light gathering ability of a lens. However, as opposed to the f number that we defined on the previous few slides, this parameter takes into account the environment in which lens operates. As you can see in the formula that's given on the left-hand side, we have this parameter n here, which represents the index of refraction of the environment in which lens has been positioned. And then also numerical aperture is defined by the half angle that basically limits the light rays that are hitting this lens. So again, the formula on the left-hand side on how to calculate the numerical aperture of a lens. Again, remember, numerical aperture of the lens represents another parameter that defines a light gathering ability of a lens. This slide gives a quick reference to the concept of numerical aperture in optical fiber. Now that we defined the numerical aperture for the lens, we also want to look at the optical fiber and see what a numerical aperture means in the case of an optical fiber. If we recall the previous lecture where we talked about optical fibers and the concept of acceptance angle, we can refer to that lecture and see how a numerical aperture for optical fiber is defined as a function of the acceptance cone. On the left-hand side of this figure, we can see the acceptance cone that's defined by the acceptance angle I sub m. And as we can see on the left, the numerical aperture of the optical fiber is simply defined as a sine of the acceptance angle. So, in the same way how a numerical aperture defines light gathering ability of a lens, numerical aperture of the optical fiber also defines a light gathering ability of the optical fiber, or in other words, our ability to launch the light into the fiber. Now that we define the lens and look at different types of lenses as well as a few parameters that define the lens, let's look at the graphical method of determining location of the image that a lens creates. We are going to be using so-called ray tracing method, similar to the one used for the mirrors. Before we go and analyze three distinct light rays passing through the lens, we also want to define a few important elements of the lens. Number one, we have a vertex, which is a center point in the positioned at the center of the lens. We also have an optical axis that's running through the center of the lens. We define two focal points, one on the left side and one on the right side, relative to the lens. And finally, we have an object that's positioned at a certain distance away from the lens. We are analyzing the propagation of the light and the creation of the image to the lens by looking at three distinct light rays. The first one, labeled as 1, is running parallel to the optical axis. And then the second light ray is running through the focal point. And then finally, the third light ray is running through the vertex of the positive lens. You can also observe that the light ray that's running parallel to the optical axis is going to be passed over to the other side in a direction towards the focal point. The light ray number 2 that's passing through the focal point on the left-hand side is going to be passed or refracted in a direction parallel to the optical axis. And then finally, the third light ray, labeled here with the number 3, the one that goes through the vertex of the lens, is going to continue without any kind of refraction along the same path. So the rule of the light propagation to the lens is very similar to the rules of the mirrors, meaning the parallel turns into the direction of the focal point direction turns into the direction parallel to the axis, and finally the one that runs through the center of the lens goes unchanged, similar to the one that goes through the center of the curvature of the mirror. The only difference is that in this case we are looking at the refraction of the or passing of the light, as opposed to the case of a mirrors where we were looking at the reflections. And then the next step, once we created the refracted light rays, is to look where these three light rays intersect in the case of the positive lens. That's our point P prime that is going to define the position and the size of the image created by the positive lens. A similar approach can be applied for the case of a negative or diverging lens. Again, we have three light rays, one that's parallel to the optical axis, one that is moving in direction of the focal point on the other side, and then third one that is going to the center of the lens, or so-called vertex. We can see that the one labeled here as a light ray 1 that's running parallel to the optical axis is gonna turn its direction so that the extension of the line of direction is passing through the focal point on the left side. And then the one that's moving in the direction of the focal point over on the other side is gonna be refracted in a direction parallel to the optical axis. And then finally the one that goes to the vertex is not changing direction. We're looking at the three distinct refracted light rays labeled as 1', 2', and 3'. We can see that they are diverging away from each other. However, if we construct an extension to the left, we'll see that the extensions are going to be intersecting at a specific point shown here as a point P', where the image that's formed by this lens is going to be positioned. To conclude the discussion on a ray tracing method in the case of lenses, again, we have been looking at the three light rays that are shown leaving an object P, and these three light rays are propagating through the lens according to a very specific rules that are shown on this slide in a yellow box. And ultimately, after they pass to the lens, they will be moving in a certain directions that would create a single point of intersection, either on the right hand side relative to the lens or on the left hand side relative to the lens. That's based on the position of the object as well as the type of the lens. It's also important to note that in practice, just two light rays are enough to determine that single point of intersection. However, the third ray is always good to be also constructed as a check of the validity of your solution. So to wrap up, the light ray that moves parallel to the optical axis is being refracted in the direction that's passing through the focal point. The light ray that's passing through the focal point on the left is going to be refracted in a direction that's parallel to the optical axis. And then finally, the light ray that's passing through the vertex is going to continue along the same path. In other words, it is not going to change its direction. Here's an example of a two-lens optical system that can be used to practice the ray tracing skills that we introduced on the previous few slides. As you can see here, we are considering two lenses. One that is shown here on the left side as a positive lens, and then a negative lens on the right hand side. It's also important to observe a specific way of drawing the positive and negative lens, so the lens does not have to be drawn by fully reflecting its shape, but very often it's shown as a line with two arrows on each side. If the arrows are shown as outward arrows, we're talking about the positive lens, and if the arrows are pointing inwards, we're talking about the negative lens. So let's look how the light propagates through these two lenses, and let's determine the position of the final image that's been formed by these two lenses or this two lens optical system. So we have the object shown here on the left hand side with the tip at point P, and as introduced on the previous slides, we're looking at the three light rays labeled in this case as 1, 2, and 3. The first light ray that's labeled as 1 is moving in direction parallel to the optical axis, and then it's refracted through the focal point F1'. And then the light ray number 2 that's passing through the focal point F1 is going to get refracted along the line parallel to the optical axis. And finally, the light ray number 3 is passing through the vertex unchanged. You can see that three refracted light rays are passing through a single point of intersection that's labeled here as a P' that defines the image formed by the first lens on the left hand side. And then that image that's been formed by the first lens is going to serve as an original to the second lens. So we are looking now at the image of the first lens positioned at a point P', as the original for the second negative lens. Here we are also considering three light rays that are labeled here as 2 and 4 and 5. So the light ray 2 that's parallel to the optical axis is going to get refracted in a direction that originates from the focal point on the left. And then we have the light ray that's labeled as 4 is moving in the direction of the focal point f2 prime, but ultimately is going to get refracted along the line parallel to the optical axis. And finally, the light ray 5 that is passing through the vertex is going to continue along the same line. So we have three refracted light rays, 2 and 4 and 5 on the right hand side of this negative lens. We can see that all three are diverging. However, if we extend the direction of propagation of these three light rays, we can see that they are going to be intersecting at a single point that's labeled here as p second. That's going to determine the position of the final image created by this two-lens optical system. Let's take a closer look at the focal length of a lens. If you recall the previous lecture, we have defined the focal length of a mirror as being half the radius of the curvature of the mirror. In the case of a lens, the mathematics is a little bit more complex. There's a few things that need to be mentioned. Number one, lens has two focal points or two focal lengths, one on the left side and one on the right side relative to the lens. And number two, these two focal lengths are equal. So the focal length on the left hand side and the focal length on the right hand side are the same. This applies not only for the symmetric lens that has the same curvature on the left hand side and on the right hand side, but also for any other type of a lens, planar convex, planar concave, with lenses that have different curvatures, etc. Again, focal lengths on the left hand side and the right hand side are the same. There's a formula that's known as Lensmaker Formula that can be used to calculate this focal length as a function of the materials the lens is made out of, environment in which the lens is positioned, as well as the radii of the two curvatures of the lens. So the formula is shown here on the left hand side, and you can see that the formula or equation on the right side has a few different parameters that have to be taken into account, one being an index of refraction of the medium that's surrounding the lens, that's shown here as n, and then n with the sub g is the index of the refraction of the material that lens is made out of. And then we also have two parameters, r1 and r2, that represent two radii of the two curvatures, two surfaces of the lens, the front one and the back one. And as you can see here, it's just one single formula that calculates one single focal length, meaning this length that you're going to calculate through this formula that's labeled here as f is going to be applied both to the left hand side and right hand side of the lens. It's also important to mention that in the case of a planar surface of the lens, in other words, if let's say the back surface of the lens is a planar, meaning there is no curvature to it, in such a case we can assume that the radius of that curvature is equal to infinity, meaning it's very, very large. So if that radius is equal to infinity, then 1 over the infinity is equal to 0. So this whole 1 over r2 term is gonna drop. So the calculation in the case of such a planar concave or planar convex lens is going to be significantly simplified. Let's now look at yet another method of determining the position and the size of the image formed by the lens. We already introduced the graphical method, or so-called ray tracing method. Let's look at the analytical approach. In the case of analytical approach, we're using so-called lens formula that you can see here. This is a formula that is similar to the formula we used in the case of mirrors. It has the same form and shape. There are three parameters in this formula, parameter P and Q and F. For F, we already know that's the focal length of the lens. And then P and Q have the same meaning as in the case of the mirrors. In other words, the parameter P represents the distance of the object from the lens, and then q represents the distance of the image from the lens. So the formula is to be used with a specific sign convention that we are going to explain on the next slide. So here are a few sign convention rules that have to be implemented while the lens is being analyzed using an analytical approach using the lens formula. So number one, we draw the optical system such as the light travels initially from the left to the right towards the lens. So the object has to be on the left side and light is traveling from the left to the right, similar to the rule we established for the mirror. So the second rule is that the object distance p is positive for real objects that are located to the left of the lens and negative for the virtual objects that are located to the right of the lens. On the other side, the image distance q is positive for the real images that are on the right to the lens and negative for the virtual images that are in front of the lens. So how can we understand this? If you remember and recall the previous lecture, we said that in the case of a mirror, the real images are in front of the mirror. That's where all the reflected light rays are going to appear. In the case of the lens, take into account that the lens is an optical component that's relying on an optical refraction, meaning passing of the light. So all the light rays that would form the image through the lens are going to be refracted, are going to be on a right hand side relative to the lens. So that's why this whole environment here that's on the right relative to the lens is considered as a real environment for the images that have been formed by the lens. So once more, if the images are appearing on the right relative to the lens, they are considered real, and in such a case that image distance q is going to be taken with a positive sign. However, if the images are appearing on the left relative to the lens, this whole environment here is for images considered a virtual environment, and images are there virtual. So in such a case, the distance q would be taken with a minus sign. Next rule applies to the focal length of a lens. It's to be taken as a positive for the converging lens and negative for the diverging lens. The radius of the curvature r is going to be positive for the convex surface and negative for the concave surface. You have to note that this is reverse of the sign convention adopted for the mirrors. And then finally, the transverse distances, meaning the vertical directions such as like the size of the object, are positive if they are above the optical axis, and they are going to be taken with a negative sign if they are below the optical axis. We can also calculate the size of the image formed by the lens. The formula for the magnification is shown here. It's identical to the formula used for the mirrors. So we can figure out the magnification by taking the negative of the ratio of the q and p, where q and p represent the distances of the image and object respectively. And then the rule for the magnification is the same for the lens as it was for the mirrors. In other words, if m or magnification is less than 1, that would indicate that the image is smaller in size than the original. And finally, if the magnification is positive, we are dealing with a real image that's appearing on the right relative to the lens. If m is negative, the image is appearing on the left relative to the lens and it's considered virtual. Let's look at a few examples where we can apply some of the techniques presented on the previous slide. Here's example 10. We are looking at a double convex thin lens as shown in the picture that's being used as simple magnifier to read a small print. So this simple magnifier has a front surface with a radius of curvature of 20 centimeters and then a rear surface with a radius of curvature of 15 centimeters. We're talking about a lens that's made out of the material whose refractive index is equal to 1.52, and there are a few questions that need to be answered by using some of the approaches presented on the previous slide. First question is, what is the focal length when used in air? And this lens is used in air. Second question is, what is the focal length if this lens is merged into water? Third question is, does it matter which lens face is turned towards the light? And finally, how far would you hold an index card from this lens to form a sharp image of the sun on the card? So to solve this problem, we are going to use Lensmaker Formula. So for the part A, we are considering this lens to be positioned in air. So our n is going to be equal to 1, which is the index of refraction of the medium in which the lens is placed. And then the ng is the index of refraction of the medium that the lens is made out of, which in our case is 1.52. Now the R1 and R2 are the radii of the two curvatures, two surfaces of the lens. The first, or front surface, is to be considered as convex for the light that's passing from the left to the right. So the radius of that front surface is going to be taken with a positive sign. However, the rear surface for the light that's passing from the left to the right is to be considered a concave, so the radius of the curvature of the back surface or the rear surface is to be taken with a negative sign. So what's left is to substitute for all these values into the Lensmaker formula and calculate the focal length. So we can calculate the values of these two fractions using the calculator. And then here these two minus signs would convert into the plus sign. Now we can add the two numbers in the brackets. And then multiply with the factor in the front of the bracket to come up with the value of 0.0607. So 0.0607 is equal to the 1 over the f. So we need to take reciprocal value of both the left hand side of the equation and right hand side of the equation. To come up with the value of 16.48 or rounded 16.5 centimeters as the focal length of this lens if it's merged into the air. As for the part B, when the lens is placed into water, the calculation is very similar, with the only difference that in the case of the lens placed in the water, the index of refraction of the medium is going to be water, and we know that the index of refraction of the water is equal to 1.33. So our Lensmaker formula is going to take slightly different shape. So we're going to have here 1.52 minus 1.33 over 1.33, and then the term in the brackets is going to be staying the same, as we are not changing the radii of the lens. So we'll still are going to have 1 over 20 minus 1 over minus 15. So if we do this calculation, we are going to have, for the term in front of the brackets, 1.52 minus 1.33 over 1.33 gives us the value of 0.143. 0.143 times, from the previous calculation in part A, we have this term in the brackets 0.05 plus 0.067, which is going to be equal, let's see, 0.05 plus 0.067 multiplied by 0.143 gives us the value of 0.0167, or for the F we have 1 over that value, which results in 59.8 centimeters as the focal length of the lens that's been merged into the water. In this second example in this lecture, we are looking at the multi-lens arrays that are used in many optical systems, very often in point-and-shoot cameras. So here we are looking at a two-lens system that's made up of a converging or positive lens followed by the diverging lens. Both of them, they have a focal length of 15 centimeters, and the assumption is that the system is used to form an image of a short nail that's about 1.5 centimeters high, standing erect 25 centimeters from the first lens. The two lenses are separated by a distance of 60 centimeters, as shown on the picture, and you are asked to locate the final image, determine its size, and state whether it's real or virtual, erect or inverted. So this is a two-lens optical system, so we are going to do a step-by-step procedure. First, we are going to be analyzing the image formation to the first lens that's labeled as L1. So we are going to use the lens formula applied for the lens L1 first. So as it can be seen for the lens L1, the object is positioned on the left relative to the lens. So we are going to take the distance of the original with the positive sign. And that distance is equal to 25 centimeters plus 1 over Q1, where Q1 is going to be the distance of the image, is equal to 1 over the focal length, and as it can be observed, the focal length for the first lens is equal to 15 centimeters. We are dealing with a positive or converging lens, so we are going to take a positive sign for the focal length. So here we can do the math. So 1 over Q1 is going to be equal to 1 over 15 minus 1 over 25, or 1 over Q1 is going to be equal to, so 1 over 15 is 0.067, 0.067 rounded, minus 1 over 25 is 0.04, 0.04. So if we subtract these two numbers, we got for 1 over Q1 0.027, or for the Q1, the value for the Q1 is, so 1 over 0.027 gives us the value of about 37 centimeters. Obviously your result may slightly different from my result based on how much you rounded the numbers during the math procedure. Now, as we can see, the distance of the image from the first lens is plus 37 centimeters. The fact that the distance is positive means that this image is going to be on the right relative to the first lens. Or in other words, this image is positioned between the two lenses. So the next step is to define the distance of the object or original from the second lens. So this image that has been created through the image formation from the first lens, that's positioned at 37 centimeters away from the first lens, is going to be served as the original for the second lens. And since the distance between two lenses is equal to 60 centimeters, the distance from this original for the second lens, or P2, is going to be simply equal to 60 centimeters, the total distance between the two lenses, minus 37 centimeters distance from the first lens to the image created by the first lens or original for the second lens. We also know for the second lens that the focal length is equal to also 15 centimeters, but in this case we're going to take the 15 centimeters with the negative sign because we are dealing with the diverging lens. And then we are going to apply the lens formula, so 1 over P2 plus 1 over Q2 is equal to 1 over F2. We're going to substitute for the P2. The P2 is going to be equal to 23 centimeters. So here we have 23 centimeters plus 1 over Q2 is equal to 1 over minus 15. And then from here we calculate 1 over Q2 as minus 1 over 15 minus 1 over 23. So 1 over Q2 is going to be equal to 1 over 15 is, in our case, minus 0.067, minus 1 over 23 is 0.0435, or 1 over Q2 is equal to minus 0.11, which gives for Q2 the value of 1 over negative 0.11, or Q2 is going to be equal to about negative 9 centimeter. Now, the fact that the Q turned out to be negative means that the image that's been formed by the second lens, or our final image, is going to be the virtual image, which is going to be positioned to the left relative to the lens L2. So once more, the final image for this two lens optical system is going to be the virtual, meaning it's going to position 9 centimeters in front of the second lens. We can also figure out the size of this final image. So the magnification, the total magnification is going to be equal to the magnification of the first times the magnification of the second lens. Magnification of the first lens is minus Q1 over P1 times the second magnification for the second lens is minus Q2 over P2. So here we can substitute for the values. You have to just be careful with all these different signs. So for the Q1 we calculated 37 centimeters. The P1 was also positive, equal to 25, and then times negative sign, Q2 being negative 9, and then the P2 being 23. So these two negative signs will turn into positive signs. So we're going to have as a final value of the sign the minus. And let's do this math here. So we have 37 times 9 over 25 over 23. We're getting the value of 0.58 minus 0.58. Now let's interpret this final value. So number one, as you can see in magnification, is less than 1, which means that the image formed by this two-lens optical system is going to be smaller than the original. And then also it's negative, which means that it is going to be positioned on the side opposite to the original. So if the original, as on our picture, the original of the nail is above the optical axis, the fact that the magnification is negative means that the image of this nail that's been formed by this two-lens system is going to be opposite to the position of the original, meaning the image is going to be positioned below the optical axis. So once more, the final image is virtual, positioned 9 centimeters to the left of the second lens. It is smaller than original. It's 0.58 or 58% of the size of the original. And finally, it's inverted, meaning it's positioned below the optical axis. And finally, as the last slide in this lecture, we want to look at so-called beam expanding collimators. A divergence is a very important parameter for the lasers. In many applications, we would want to reduce the divergence of the laser. What do we mean by the divergence? By the divergence, we mean that the diameter of the laser beam is expanding as the laser beam is moving away from the laser. So certain applications would require a laser beam with a low divergence, but at the same time a significant beam width. So if you look at this optical system here shown as a Galilean, you can see that on the left side you have the laser beam that's very narrow and it does not diverge that much, meaning if you take any kind of cross section along this laser beam, you can see that diameter of the beam is the same. However, what we want to achieve over on the other side is much wider laser beam, but at the same time the beam that does not diverge, meaning its diameter stays the same. So the purpose or the function of this two-lens optical system that you can see here, that's known as beam expanding collimator, is to expand the beam, but at the same time to maintain its divergence. So a beam expander consists of two lenses, one being a diverging and one being a converging, that are positioned at a specific distance from each other. So the first beam is diverged with a short focal length lens, and the diverging beam is then recollimated with a larger beam waist and smaller divergence. So after passage through a beam expander, the divergence of the beam is equal to its original divergence. You can see here that again the beam width is always the same, it does not change, and then also here the beam width does not change, but it's significantly expanded. It turns out that these two lenses, in order to provide for the beam collimation, they have to be put at a distance that is equal to the sum of their focal lengths. Now keep in mind that one of these two lenses, the diverging one, is going to have a negative focal length, while the other one is going to have the positive focal length. And then we can also define a ratio of the beam widths at the output and at the input as the ratio of the focal lengths of the two lenses. We have come to the end of this lecture. In this lecture, we looked at the image formation with lenses. We considered a few different types of lenses. Then we analyzed the ray tracing method through the lenses, as well as the Lensmaker formula to calculate the focal length of a lens. And finally, we used analytical approach to determine the position and the size of the image that's been formed by the lens. At the end of the lecture, we also took a closer look at so-called beam expanding collimators that play an important role in many photonics labs where an expansion of the beam width is required at the same time the beam divergence is maintained. As we are slowly moving towards the closure of this lecture, I also would like to introduce the next lecture, which is going to be the review of the material that we covered in the previous as well as in this lecture. So we are going to look at the ray tracing method again, both for the case of different mirrors as well as a few different types of lenses. So that material again is going to be the review of what we introduced in this and the previous lecture, as the graphical ray tracing method turns out to be the most difficult subject for many students. So that's why we are going to take a step back with the next lecture and do a little bit of a review before we move on to the next subject, that is going to be the physical optics.